Logarithmic differentiation is really just a fancy term for taking the natural logarithm of something and then differentiating it. Before we get into this, the ingredients for a logarithmic differentiation are properties of logs. For example, you need to know that the log of a product is the sum of the logs, ln x, ln y. You need to know that the log of a quotient is the difference of the logs. You need to know that exponents of, say, a to the x. Exponents pull through logarithmic expressions as coefficients. And lastly, you need to know that the derivative of the natural log function is 1 over x. And you need to know how to apply the chain rule with this. And you need to know how to expand logarithmic expressions without having to really think about it. Now, all these, of course, these three hold true for all logs. This one is, of course, only the derivative of natural log, but that's the only one that we're going to need. Alright, so to illustrate this, the first example I have is this. Right, we want to differentiate the natural log of this nasty looking thing here. So, at first glance, what you might think is that you would say, all right, the outer function is the natural log, so the derivative is going to be 1 over all this mess. And then by the chain rule, you would have to multiply that by the derivative of this. But that's going to take a lot of work, right? Because there's a product on top, and the things are complicated looking, and it involves a quotient rule, and there's a trig function, and everything is messy, right? You got f prime g, g prime f, and there's chain rules and all that stuff happening, and it's just a big mess. So, but if you're smart, what you can see is that you can break this expression up with the logarithm because there's a log sort of pre-made in there. So this function, let me just break that up. So we'll be actually taking the derivative of, by properties of logs, it'll be ln x plus ln radical x plus 1 minus ln of sine x. Alright, that's one way to go. When you break these things up, everything that's on top is going to get a plus sign associated with it, and everything on the bottom is going to have a minus sign associated with it. After that, we can actually, don't forget to bring out all the powers, including this. So we have ln x plus this square root, since it's over the entire argument. This is actually like x plus 1 to the 1/2. So this gets pulled through the front just to simplify things up a little bit more, and that leaves you with x plus 1 on the inside minus ln sine x. Right. So it breaks up like so. And now we didn't do anything yet. We didn't differentiate it yet, but now it's easy, right? Because you have more functions, but there's a whole lot less work involved. Because the derivative of that is just 1 over x. Right, the derivative of this is going to be plus, we'll have 1/2 1 over x plus 1 minus right, it'll be 1 over sine x times the derivative of sine, which is which is just cosine x. And so this would just simplify up like this: 1 over x plus, say, 1 over 2x plus 2 minus the cosine over the sine would be cotan x. And it would go just like that. Now that, I did out every step, but even still, that's a lot less work involved to get the final answer than, rather than having to go through this thing the long way. I suggest that you try it. But that wasn't actually logarithmic differentiation because the log was already in there. So the technique of the actual process of doing this comes when you have to differentiate something that's a big complicated mess like this. Let's see. When you hit, what you do is you log both sides. You hit both sides with a natural log, and it'll break this apart into a bunch of little pieces, all of which individually are easier to differentiate than the whole. So what you do is you take the ln of both sides, so it'll be ln y equals ln of that whole big thing. And what's going to happen is, because of properties of log, this is going to break up. So how many pieces? It's going to break up into one piece for each sort of thing that's being multiplied or divided here. So if you box them off like that, we'll have 4 of them. So the ln of these 4 things actually equals the ln of individually, that'll be 3, plus, now it's going to be ln of x to the 4th, but the 4 is going to pull out as an exponent, right? The ln of x to the 4th, which is actually 4 ln x, and then the things on the bottom get a minus, so that'll be minus. Sine cubed of x is actually, the exponent is going to pull out, and we'll get 3 sine x. And this one here, the same thing is going to happen. The 5x as the exponent is going to pull out front, and it gets a minus sign again because it's on the bottom. And the last one will be minus 5x ln of e. This was actually an ln of sine x also, right? 4, right? ln 3, 4 ln x, 3 ln sine x, and 5x ln a, right? So once you have it like this, breaking it up is actually, I think, harder than doing the actual log, but I mean the actual differentiation. But if you just now we just differentiate implicitly on this side, and this side you just do as normal. So the derivative of ln y is, it'll be 1 over y dy dx equals, and when you do these individually, ln 3 is just a constant, so that's going to drop away. It's going to be nothing. 4 ln x differentiates to 4 over x. Minus 3 ln sine x is going to differentiate to, it'll be minus 3 1 over sine x times, by the chain rule on that, cosine x. Minus 5x times, now the ln of e, the natural log of e, is 1. So this is just a 1, so we can feel free to ignore that. And the thing hanging off the end is just a 5x, whose derivative is just minus 5. All right. So that's it. Differentiation is done, and the last step in all of these is to bring over the y, so that the final answer I'll write as dy dx equals, and what would it be, 4 over x minus, let's see, you got cosine over sine, so I'll say that's minus 3 cotan x minus 5 all times y. Now you have the now this looks pretty simple. I guess the price that you pay for the easy differentiation is that there's going to be a y in the derivative, but that's actually that's not really that big of a deal, because if you say that you had to do one of these derivatives anyway, something this complicated at least would be involved in doing out the answer if you needed it at a specific value of x, say. So it's really not a high price to pay for getting the derivative. But it's only one example. I have a few more. See, all right. So there's this mess, and so when you see it's really complicated like this, we got 1, 2, 3 terms. They all have powers. It's going to be nasty. This, you would say to yourself, this could be a candidate for logarithmic differentiation. So what you do is you log both sides, and you'll have ln y equals ln of that whole thing. And so let's just go over quickly how many pieces it's going to break into. We'll have 1, right, x to the 4th, the tan cubed, and this thing down here. And now, just to be aware, the coefficients in the product in the full expansion, the 4 is going to pull out, the cube is going to pull out here, and this, the radical, is going to come out as a 1/3. So we're going to break this into 3 different pieces. So we'll bring it down. We'll have ln y equals, this will be 4 ln x, right? Plus, because it's on top, the 3 is going to be brought out front, so 3 ln of tan x. And then because it's on the bottom, we'll have a minus, but the third root is to the 1/3 power, so, and that's going to come out in the end as a 1/3 ln of the quantity x squared plus 1. So we've taken the log of both sides and just broke it up. And now we just differentiate with respect to x. You'll always have to do it implicitly on this side. That'll be 1 over y dy dx again. dx equals, once again, 4 over x. Right? This will be 3 plus 3 times. It'll be 1 over tan x times the derivative of tan x, which is secant squared x, minus 1/3. The derivative of the outside is 1 over, so 1 over x squared plus 1 times, by the chain rule on the inside, 2x. And let me just see if I can make that a little bit neater. What will it be? It'll be 4 over x plus 3 secant squared x over tan x minus 2x divided by, say, 3x squared plus 3. Alright, nice and neat. And once again, at the end, this was equal to 1 over y dy dx. So the last step is to multiply through by y. Let me just put some colors around that. Just tack a y on the end of that. And that's it. That's your dy dx. Right, logarithmic differentiation. Now, we didn't have to do logarithmic differentiation on this. It could have been done without doing logs at all. We just chose to use logs for it because it makes the job a little bit easier. There are, however, some cases where you have to do logarithmic differentiation in cases like this. Now, briefly, I want to go over what sets this apart from other functions. If you have a function, say, like y equals 3 to the x, or y equals, say, x to the 4th, or y equals, say, pi to the e, right? These functions, to differentiate this, you treat it like it's an exponential. All right? You know that the derivative of this is 3 to the x ln 3. So it gets its own special rule because it's exponential. This is just the power rule that we know and love for x cubed because it's a polynomial, and we use power rules on the polynomials. And this is just a constant, so its derivative is going to be 0. Now that's constant to function, function to constant, and constant to constant. All these we know how to handle. This last category is when you have a function raised to the power of a function. This is what necessitates logarithmic differentiation, because it's the exponentiation that we don't know how to handle, right? Both base and exponent are functions of x or have x's in them. So, I say to use logarithmic differentiation is because what we're going to do is we're going to capitalize on the exponent property of logs. When we log both sides, you get ln y equals ln of x to the x. What we have is this exponent pulls out, and what you always wind up with in these problems is just a ln x is a product rule problem. You take the exponentiation and turn it into some kind of a product rule. Now, this is how it's done. This is the technique for when you have function raised to function. You have to do logarithmic differentiation. But all that you do is just log both sides, and then just differentiate implicitly like we just did with the other problems. Again, there's a 1 over y prime equals the product rule. So f prime g is ln x plus g prime f. Now g prime is 1 over x times x is 1. So the final answer is y prime equals ln x plus 1 times y. Or because this one is so simple, I like to write y prime equals, we'll have ln x plus 1. In this case, I will rewrite what y was. I'll substitute it back in. What used to be y was x to the x. And that's how you use logarithmic differentiation for bases and where base and exponent are functions. And I have a couple more examples of these. X to the x is the most basic one. Everyone does that one first. Or if it's more complicated, like so. Still, not a big deal. You recognize it as a candidate for logarithmic differentiation and then just log both sides. So you have ln y equals, when I will write it out. We'll have ln of x squared plus 2 to the quantity of tan x. Alright, but by the properties of exponents and logs, the tan pulls out, and we have our product rule, tan x times the ln of x squared plus 2. Alright, so it turns the exponentiation into a product. Differentiate implicitly, once again, 1 over y dy dx equals f prime g, so the derivative of tan is secant squared x times ln of x squared plus 2 plus g prime f, the derivative of log is 1 over x squared plus 2 times, by the chain rule on the inside, right? This is the outside, the inside is 2x. And then to complete the product rule, tan x. You still see that? Yep. So once again, the final step is to multiply through again by y, and for this one we'll have dy dx equals secant squared x ln of x squared plus 2 plus 2x tan x times over x squared plus 2, all multiplied by the original expression, right? The x squared plus 2 to the power of tan x. And the last example I have is with non-specific function, just f of x. This is pretty much as crazy, I think, as they're going to get. But you handle it just the way you handle all of the other ones. Just log both sides. You'll have ln y equals, now the natural log of all this, the 2x as the exponent is going to pull to the front, and we'll have 2x ln of f of x cubed. Alright, so now differentiate implicitly 1 over y dy dx equals 2 times, I'm going to just ignore that 2 and kind of treat it like this. Right? So f prime g, so that's easy, that'll be just ln of f of x cubed, whatever that is, plus g prime, this is the product rule with this and this. Alright, so the g prime, the outermost function is the log, so it'll be 1 over f of x cubed times, by the chain rule, f prime of x cubed, and then to finish off the chain rule, times 3x squared. Right, it's a chain of order 3. It's the log, then f, then the x cubed. So that's f prime g plus g prime is this whole thing, times f is just x again. And the last answer would be, once again, last step is to bring it over the y, and you'll get dy dx equals, if I throw that 2 back in, it'll be 2 ln of f of x cubed, plus when I distribute the 2 to this term here, that will combine with the 3 for a 6, 3 x's, so 6x cubed, f prime of x cubed, divided by f of x cubed. And all that multiplied by y. front. So there you have it. That's logarithmic differentiation. I will briefly mention that sometimes another way that you might see this, instead of taking the log of both sides of an equation, what will happen sometimes is some teachers will tell you to take one side and exponentiate it and then take the logarithm of it. For example, it's going to happen like this. If you have y equals, say you'll have f of x all raised to the power of g of x. What they like to do sometimes is they'll log this, they'll just log this side, but then they'll exponentiate it with e at the same time, so as to it would be kind of like adding and then subtracting 1. It doesn't change the value of the expression, it just writes it a little bit differently. And what you would get is, we'll use the property of x equals e to the ln x. Right? E to the ln x is x. This is an identity. So the x is what we're going to make the f of x to the power of g of x. Right? So it'll be like this equals e to the power of ln of f of x to the g of x. I know that's really small up there, but inside here, right, again, the exponent power of the log brings this out in front. So what you're going to have is this will actually be equal to e to the g of x times ln of f of x. So, and that equals y. So the reason why this has the same effect is, if you you don't have to differentiate implicitly, but when you differentiate this side, you'll get y prime. When you differentiate this side, the first step in that process is going to be the exponential function. So that's going to be itself, which is e to the g of x ln of f of x, multiplied by the derivative of this expression here. And if you notice, what happened in all these examples was the logged version, this was like g of x. Wait a minute. This was like g of x, right? That was the exponent. And this was the f of x. So it's, just this inside here. So it would be g of x ln f of x, right? This is the f, this is the g. And the derivatives all work out the same. This is just the y from the original equation. You know how the last step is to finally, once you get to here, you take the derivative of that thing, which is the g of x times ln of f of x, and then you multiply it by y. That's this popping up in there. So it really is the same thing, and at the very end, what you could do with this mess is simplify it back to what it was originally. But that's how some other teachers do it. The way that you do it for me doesn't really matter. But that's going to wrap up the lecture on logarithmic differentiation.